In this section, we'll talk about the geometric interpretation of dot product. In the last section, we defined the dot product of two vectors to be equal to the sum of the products of the corresponding components. Now we'll see the geometric meaning of that definition. Let's suppose theta be the angle between the vectors A and B, which is defined to be the angle between the representation of the vectors A and B that start at the origin, and the angle has measure 0 to pi. So if we have two vectors that are parallel to each other, their angle in between could be either 0 or pi, according to whether the vectors are parallel in the same direction or the vectors are parallel in the opposite direction. Now discuss the figure. We have a vector A whose representation is the line segment A, and we have another vector B whose representation is the line segment OB. And then the directed line segment BA is the representation of the vector A minus B, because if we add this vector with this vector by following the triangle law of vector addition, we simply get B plus this vector A minus B, which is B plus A minus B, which simply gets us the vector A, the resultant OA. Now we have a theorem. If theta is the angle between the vectors A and B, then the dot product of the vectors A with B is equal to the product of the magnitude of A and the magnitude of B and the cosine of the angle between them. Recall that the theta has measure 0 to pi. Let's start the proof. So we start the proof with the statement that the dot product of the vectors of A minus B with itself is simply this. We obtained this by applying the properties of the dot product, namely the distributive property. For example, the A dot A gives us the A dot A, the first term here in the right hand side, and the A dot B with a negative sign, it's negative A dot B. And similarly, if we multiply the inner vectors, for example, the negative B with A, this gives us another term. Since we know that the dot product is commutative, so B dot A can also be written as A dot B. So we had another term earlier, A dot B. Now we have B dot A. So we have two such terms here. And the very last term is the B dot B with a plus sign here. The first term is simply the square of the magnitude of the vector A. So is the last term. So we put this as an equation 1. Now we apply the law of cosine to the triangle as shown here to obtain the equation this. So let's discuss the law of cosine. The law of cosine says, so if theta is the angle between the vectors, then the square of the magnitude of this vector, which is A dot AB, the square of the magnitude is equal to the square of this side, the magnitude of this vector, which is OA, plus the square of the magnitude of this vector OB, minus 2 times the product of the magnitudes of the vector A and the vector B. And the cosine of the angle between them. This is called the cosine law of the triangle. Let's apply this law to get the equation as shown here. Now, the left-hand side is simply the square of the magnitude of the vector A minus B, since A, BA, or AB both have the same magnitude. And OA is the representation of the vector A, so it's the square of the magnitude of A. And similarly, the square of the magnitude of B minus 2 times the magnitude of A, the magnitude of B, and the cosine of the angle between them. Now we also know that the dot product of the vector A minus B with itself is simply the square of the magnitude of A minus B. It's simply any vector A, the dot product of with itself is the square of the magnitude of itself. So you have the vector A minus B, we have the dot product with itself, we get the square of the magnitude of the vector. So in equation 2 and equation 1, we see the left-hand sides are equal, so the right-hand sides also must be equal. So equating the right-hand side of 1 to the right-hand side of the equation 2, we get this. Negative 2 times the A dot B equals the negative 2 times of the products of the magnitude of A, magnitude of B, and the cosine theta. If we cancel the factors, negative 2 from both sides, we get the required expression. This is the end of the proof of the theorem 3. Before we see an example, we have an important corollary of this theorem. Corollaries are the direct consequences of the main theorems. It says, if theta is an angle between the non-zero vectors A and B, then cosine theta can be expressed in this way. It is a simple consequence. From this equation, we can see that if we solve this equation for cosine theta by dividing both sides by the product, the magnitude of A and the magnitude of B, we simply get this corollary. Let's see an example. We need to find the angle between the vectors A and B, whose components are as shown. We can use the formula here, and the formula requires that we need to know the dot product of the vectors and the magnitudes of each of the vectors. So the dot product of these two vectors is 2, and the magnitudes, the product of the magnitudes is 3 times the positive square root of 38. If we solve by using our calculator, then we get the theta value as 1.46 radians, or 84.79 degrees. Orthogonality. Two vectors are called orthogonal or perpendicular if the angle between them is pi by 2 radians, or 90 degrees. Now we have another corollary. It says that two vectors are orthogonal if and only if the dot products of them is equal to 0. So note here, this is an if and only if statement. It means if the vectors are orthogonal, that means that the dot product would be 0. On the other hand, conversely, if the dot product of these two vectors is 0, then the vectors must be orthogonal. Let's see the proof. So let's begin. Let's start proving the forward direction. If the vectors are orthogonal, then their angle between them is pi over 2 degrees. And just by applying the previous corollary here, or the theorem, we simply get this equation. Since the cosine of pi over 2 is 0, this is 0, we get the entire product 0. So if two vectors are perpendicular or orthogonal, then their dot product is simply 0. Conversely, if we assume that the dot products of these two vectors is 0, then by applying the corollary of the previous section, we simply get this equation. The cosine theta equals the dot product of the vectors. This is the dot product. So this is the dot product of the vectors. And we have the magnitudes in the denominator. But in the end, we get 0. The cosine theta becomes 0 if theta is pi over 2. Let's see an example. When it showed that these two vectors are orthogonal to each other. And this can easily be shown that if we get the dot product of these two vectors 0, then by the previous corollary, that the vectors must be orthogonal. So the dot product of A with B is simply 1 times 5 plus 2 times -1 plus 3 times -1, which is equal to 5 minus 2 minus 3 equal 0. We are done. The dot product can also be used to know whether the angle between the vectors is acute or 90 degrees or obtuse. Notice the angle between them is acute, means the theta has measured from 0 degrees to 90 degrees. So in between, strictly in between 0 to 90 degrees. And if it is 90 degrees, we say the vectors are orthogonal. And if it is larger than 90 degrees but smaller than 180 degrees or pi radian, we say the angle is obtuse. So we can easily show that if the dot product of the vectors is positive, then the angle between them must be acute. And as shown in the previous section, if the dot product of these two vectors is 0, then the angle between them must be a right angle or pi over 2. If the dot product of the vectors is smaller than 0, means negative, then theta must be obtuse. Let's see an example. We need to decide whether the angle between the vectors a and b, whose components are as shown, are acute, or right, or obtuse. Let's solve this problem. Since we can calculate the dot product, for example, a dot b is simply 1 times 5 plus 2 times -1 plus 3 times 0, which is equal to 5 minus 2 plus 0, which is 3, which is surely a positive quantity. So the angle between them is acute.